Yeah, now we are going to look into a norm, a specification that is specifying how you control functions or control functionality in a controller or an automation device of sort. You normally a programmer controller. Again, it's going to be the compendium, and we are going to look at this norm, which is called IEC PAS 63131 2017. This is a preliminary norm, but there doesn't exist a lot of specification how to program, let's say, control functionality in programmable controls and so on. So this deals with safety and automation system as SES systems, so how to control those. It's based on other standards. It's based on PNID norms. The ISA is 5.2 or something like that, and also this norm here for programming PLCs. So there is some terminology. We are going to look at this figure here. So the functionality, this norm specifies two types of functions. They are input or cause functions and output or effect function. Input functions handle sensor, effect functions handle actuators, and so on. And they also specify an HMI interface. What should you be able to do this stuff? Because an output function could be motor control, a motor controller. Input function could be something that scales and reads an analog measurement or something like that, and presented to an operator and so on. There are actions alarm from sensors that can lead to safeguarding actions in these output functions. So we're going to look at that a little later. The modes, what we have looked at in earlier videos, is manual and automatic mode, and they are here too, but they have an additional mode, outside mode. We looked at local mode, but outside mode have two types. Outside mode, there is control by your automation device or PLC, but control is initiated not from the operator station or not by automatics in your controller, but by input to your automation device. Maybe it's a display or push buttons or whatever. That's what they call outside control mode. Manual control mode and automatic control mode. These we have talked about. Manual mode, effect objects are operated by an operator on an HMI screen. Automatic mode, it uses a sensor or something, whatever. It uses information from the automation device program to do whatever it should do, start and stop a motor or whatever. So that was automatic. There's also some called internal and external set point modes for controllers. A controller, PID controller, as an internal set point. The set point is entered by an operator on an HMI system. External is calculated by some logic in your controller here. Alarm types, they define action alarm, warning alarm, and fault alarm. Action alarm leads to action in the process. Warning doesn't do anything to the process, but maybe the operator should do something to mitigate the problem or whatever. He has a fault alarm is faults in your system. Basically what it is. And then it defines states for devices. And they use high, low, and confirmed position or confirm state or whatever. High state, active. Valve open, motor running. Low, passive. Motor stopped, valve closed. Confirmed position, I've commanded the motor to start, it is running. It's confirmed. Then it's confirmed high. Confirmed low, I've commanded the motor to stop, it is stopped. So that's about this confirmed position. Then we have safeguard and disable. Safeguard is forcing output functions to force the device, field device, to a set state, high or low. Disable, preventing my process device or device in the process to go to a state high or low. And then there are two types of safeguard. If you force it, say go to high state. If the force is removed and the automatic says, for instance, it should go to the low state, it returns to low state. If you lock it, then you say, okay, go to high state, lock in manual. So if the state forcing it to high state, or the condition forcing it to high state disappears, it remains in high state. And the operator has to put it in automatic mode, and it returns to low state, or he can close it in manual mode from the screen. This is nice. Then we have suppress and blocked, and the suppress is basically blocking or inhibiting actions, and suppress for let's say an input object is there's no action output from the object, and you don't get any messages, and so on. That was suppress. Yeah, and block is for an input object. You block the outputs, but you get messages. And then block for an output, suppress for an output function is what you just treated as normal, and block for an output function is you block safeguarding actions. I think it's about what it says here. And conflict is for an output function. It says it can be also a PID controller, but output your logic says you should be open, but your safeguarding action says you should be closed. There's a conflict in your system. You have to report it. Then the operator should look into this and say, okay, maybe you should block the safeguarding action and open it no matter, whatever, and so on. Then they have something called system control diagram, and this is what's important, because here what this norm says, we specify functionality for a safety and automation system. So we get, let's say, so we know, desired. So we achieve the desired functionality for control system. So everyone working on this system knows what's required for the system to work. They have function templates. We are not going to. You can read these two here. So what they have motor control. If you look at that one, we have talked a lot about motors. They have SBE, switch binary electric motor. V for valve, coordination, duty standby. The CA, since we talked, is continuous control. It's basically PID control, but they call it continuous control because if this evolves, maybe there's another type of controls. Maybe it's a fuzzy controller that you can embed into this continuous control. But then they specify tuning by P, KP, TI, and TD, and PID parameters. So they would have to change it. And there's a coding matrix. So if you look at the coding matrix, you are going to find these names. And if there should be a serial communicated signal, binary signal, should be called MBS. Doesn't exist. Yes. And here is an example for an output function. This motor control. See quite a bit here. Here are lock safeguarding, close. We're talking about safeguarding, disable, force block, force suppress. The block and suppress can be performed by or from the operator station too. And here is for this coordinated SPC information. Here are the outputs, normal function output, and we talked about pulsed outputs earlier in an earlier video, where we latch the actuator so we can start a motor. If my automation device dies, the motor keeps running, and I need another pulse to remove the latch and stop the motor. Specify this binary confirm we talked about, automatic mode, auto mode, and so on. And here is just a copy of the inputs states of these inputs there, the set type. They are just transmitted through. And there's extensive description of the functionality for this object. So they have pretty elaborate function, and then they use these terminal names here. It's also constructed based on a terminal naming matrix, code matrix. So we looked at lock automatic, lock, L, lock command, A, auto mode, automatic mode. XGH, I think, was here too. X, external input. G, we use that for position. And H, high. The component is active. Motor is running, valve is open. And so on. And if you want to program according to this, you can just look at this matrix and maybe you can make your own names. The reason why is also that in most programs you use a graphical tool to configure your program. It's called CFC, Continuous Function Chart. And if you have long names here, you have to read and decode and say, okay, let's say running, that's fine. Active, what is active for this component? So we use these codes here. And there's not a lot of codes, so they're easy to learn. So if you've been working with this norm a while, you know XGH, okay, it's active, it's doing something. It's also working on positive logic only. So positive XGH means active. So it doesn't mean you don't use an inverter here. So the functions here internally, they're working on positive logic only. So if you only have a stop feedback or closed feedback, you have to invert it to make the high feedback, because the stop is in positive logic and the high would then be in positive logic. And the SCD here is just a small example from an SCD. It's a structure control diagram, I think it's called. Yeah, look it up. So here we have two functional templates, so functions and monitor analog we talked about, cause and action alarm low, low. Here we have a valve that has a lock safeguarding low input, which means forces this one shut. This symbol means with the arrow down means that's fail closed. So, okay, low tank level, shut valve. Makes sense. Don't let the tank run empty if that's important. So that is an example. So this was about this norm. There is not a lot of norms existing for how to program functionality in automation systems. This is made for the Norwegian offshore shelf, installation on the Norwegian offshore shelf. And it's been made by Equinor, the Norwegian oil company. But it's based on 30 years, so 30 or 40 years or more of experience. And you can, if you have these components, they work fine in onshore plants too. There is adequate functionality in these components to control most of the components you would encounter in an onshore plant too. So there's not a lot of norms specifying this functionality. And it's used by engineering companies to specify functionality for a plant. And these SCD specifications, they are handed over to, let's say, the safety and automation system suppliers for the programmers to program this functionality in a PLC or automation device of some sort.